All right, folks, we're going to talk today about some key features of functions. Okay, some key features of functions. A lot of this PowerPoint that I've got here is, it's a new section, but a lot of it's redundant. Okay, my main task here, so the redundancy part is talking about domain and range. Our main task is to first identify, how do we graphically interpret inequalities. And then once we do that, talk about increasing and decreasing functions, and then determine local maximums and minimums. Okay, so that's the task at hand. These concepts are not extremely difficult, okay, but they are pivotal concepts for the remainder of the class, and they are the key components to a lot of calculus that we're going to maybe experience later on. All right, so scrolling through this, I'm going to find, where's the question? Okay. Talking about how to compare two graphs as an inequality. Okay, don't write that down. It's a lot to write down. I don't think it's necessary. When we're interested in determining where two graphs are unequal, or two functions are unequal, okay, the number one thing to do is find where those two functions are equal. Okay, and we've talked about this. So you've heard me say this before. We're going to find out where they are equal, and then by default, everywhere else they are unequal, right? And then there'll be a short, quick test to determine how they are unequal. Okay, so this here is the concept that we're trying to kind of justify. Okay, it says the solutions of the equation f of x equals g of x. All right, we've talked about how every equation we ever come across, the left-hand side is a function, the right-hand side is a function, and if we graph them separately, okay, we should get, maybe something's linear, maybe something's quadratic or whatever, and then we graph them both together. A lot of times they cross, right? Or they intersect. The solutions to the equation are the x values where f and g have the same y values. Does that make sense? The x values where f and g have the same y values. That's ultimately where they intersect. Okay? So if we know where they're equal, and so looking at our picture down at the bottom left, we're talking now about lowercase a and lowercase b, those being the x values of where f and g are equal. Okay? The f of a amount, whatever that y value is the same as the g of a amount. Okay? F of b, whatever that y value is the same as whatever g of b is. Does that make sense? So for the same x values, maybe a or maybe b, if we get the same y values back when we evaluate, those two functions are equal. Okay? Now, if that's where they're equal, then could we agree that everywhere else they are unequal? Yeah. Okay? So that's what the right picture is saying. And that's what the second statement here is saying. The solutions of the inequality, f of x is less than g of x. Well, that said, and there's several ways of phrasing this. They say that means for those x values, that is where g is higher than the graph of f. Well, if it's higher, that means the g of that x value is greater than the f of that particular x value. Does that make sense? Okay, if I were to look at this interval a to b, okay, a to b, they're saying that g is greater or above, or they use the word higher, than f. Okay? The reason for this, if I were to figure out what that y value right there was, and figure out what that y value right there was for maybe that x, okay, would you agree that, so that's called g of x, that's called f of x. I put that subscript there, so might as well, let's actually get rid of that. Don't worry about it. Either x or x sub 1, whatever. But you can make the argument that the y value, g of x, is bigger than the y value described by f of x, right? And if that's the case, then you know that your g of x is greater than f of x, okay? Everywhere in that red interval from a to b, that relationship is going to exist, okay? Now, the places I chose, that might be the greatest kind of discrepancy between those y values. But if this x is here, okay, we still have that relationship. Now, it's a smaller discrepancy, right? But it's still g of x is bigger than or larger than f of x. Okay? So that's how we graphically determine these things. In your homework, they're going to ask you to graph some of these things and make arguments about specific equations. So they're going to do this. They're going to give you 3 parts. Okay. My hope is that we don't approach this like it's 3 separate problems. Okay. First one they're going to give you is the actual equation. See where they're equal. Okay. Now, they should be giving us, for the most part, things that we can figure out algebraically. We can find out where those 2 things are equal algebraically just by solving the equation, right? Just by factoring here. However, I think it makes sense maybe to graph it a little bit. And I've got a lot of stuff on here that initially I don't want to have on here. So let's wipe some of this stuff away. All right, so we graph the left-hand side of that equation, which was 2x squared plus 3, that green function f. And I graph the red one, which is the right-hand side, f of x plus 6. Make sense? Those 2 graphs cross each other, okay, they intersect, which means to us that, okay, at those 2 x values, okay, so I find the intersections, and then I go down to see what are the x values of those intersections, okay? And over here you can see that the x value of point A is negative 1/2, and the x value of point B is 3. So those would be the solutions that you find to that first equation if you're working out algebraically, right? That is where the 2 things are equal, okay? Well, if that's where they're equal, that effectively breaks up our domain into 3 intervals. So let's look at I don't know. Can you guys see if I use that yellow? Not real great. Better? All right, so would you agree that these x values of negative 0.5 and 3 take our domain, which is our domain for this function, both these functions are all real numbers, okay, and it breaks it up into 3 sections, okay? Well, those 3 sections are where now the graphs are unequal, okay? And if I want to talk about how they are unequal, what I'm going to do is I'm going to choose a particular x value. Okay, and my x value is going to be this slider right here. Okay, so if I pick that x value of 1, so m is the x value that I'm choosing. If I pick it to be 1, right now we're seeing in that purple region, is g of m bigger or smaller than f of m? It's bigger. G of m is bigger. So if I actually asked, I think we can actually ask this to find what f of m is and what g of m is. Okay. So this is f. Is that right? Yeah. So this is f, and this is g. And you see that the g is 11, that y value is 11, and this y value is 5. Obviously, we can make that argument that this one is bigger, right? Is that the same behavior everywhere, kind of in that pink? Well, I zoomed in and out. There we go. Is that the same behavior everywhere in that pink range or interval?
Yeah.
Yeah, okay. Now they become equal right there. But as I go over here, now f is now a larger y value than what g is, right? Does that make sense? So over there, we would say this is where f of m is greater than g of m. In the middle, it's g of m greater than f of m. And then to the right, okay, to the right and over here, we're back to f of m being bigger than g of m. Okay? Does that make sense, everybody? So the argument is when they ask you these questions in your homework, do not attack that as three separate parts. Okay? Solve the first one, find your intercepts or your intersection points. And we did this a little bit the other day with a sign chart. Okay? Think about now the right-hand side was 0 in our sign chart. Okay? But when we found our zeros, we put those positions on our horizontal line. You guys remember doing that? Give you a quick reminder here. So we had some function f of x, and we had to make it greater than or equal to 0. We solved that, and it gave us some zeros. And maybe that 0 was negative 0.5, and let's just say 3 like the last one. And we went through here, and we try to find like plus and the minuses. Maybe it was plus and plus. Maybe it was plus and minus there. So the total would have been negative here, positive there, negative there. You guys remember doing that?
Yep.
Okay. What that is doing for us is ultimately taking a y value and comparing it to 0. Does that make sense? Another y value. And in that middle region, we're seeing that the y value that we're finding is greater than 0. So that means that that's the interval we'll be looking for, right? And then that f of x is greater than or equal to 0 aspect. Okay? To the left of negative 0.5, we're saying that the y value that we found was negative, so it's below the function f of x equals 0. Does that make sense? Okay? So that is effectively the same thing that this explanation was talking about. Okay? But instead of comparing maybe this green one to the red one, we'd be comparing the green one to maybe the x-axis, okay, or the line y equals 0. So we've been using this concept already. But the idea is to find where they're equal. If you find where they're equal, you know automatically where they're unequal. And if you can find one interval or all the intervals in which maybe 2x squared plus 3 is less than or equal to 5x plus 6, if you can find the intervals where that is true, where part B is true, then aren't all your other intervals where C is true? That makes sense? If I asked you two questions, I gave you the statement, or maybe it's just one question. It's 70% chance it's going to rain today. And I asked the question, what's the probability that's not going to rain? 30%. It's everything else, right? We call that the complement and probability, right? Okay. Well, when you find equality, and then you find less than, okay, then everything else has to be the complement of those things, which would be greater than. Does that make sense, everybody? So my hopes are that when you see a question like this, you don't do all three parts. You do the first two, okay, and you realize that, well, if I know where everything's equal to and where I know everything was less than 2, and I still got some of these other intervals existing that I haven't defined yet, that must mean where they're greater than. Okay? Is that cool?
Yes, sir.
All right. So the rest of this, oh, didn't want to do that.
Wait, so is the only way to like do it graphing it?
Right now, I would suggest that, yeah. When you get to your homework and they ask you to talk about ask about these inequalities, they will probably say using the graph or using a graphical approach, figure out the intervals of where this function is less than or equal to that function.
So do we usually like that?
Use Desmos, use GeoGebra. If you want to use UTIA 384, you can. Those are just
Harder.
yeah, they're kind of garbage. So, The next thing I want to talk about is hopefully that was something we've already discussed. Okay, I just wanted to hit that topic one more time. This here is a very, I think, fundamental concept, but it's almost like it's elementary. It's obvious. It's common sense almost. Okay, but it plays a big role in mathematics from here on out. Okay. And a lot of the things that you learn in a calculus class are actually going to streamline this process. Okay? But it's very useful to know where graphs are increasing and decreasing. You know, a lot of times maybe like a business will take its data points, okay, of maybe sales and profits or cost and profits, revenue, that kind of stuff, and they will plot that. And they'll come up with this logistics curve. And they'll talk about then, okay, well, where are we increasing? Where is our profits increasing? And then talk about, okay, well, between these two key points that we're increasing, and maybe those key points were maybe their number of manufacturing, okay, their quantity of manufacturing items. And say, well, okay, we need to stay inside these confines. We need to maybe manufacture 1,000 to 1,500 items so that we maintain an increasing profit. Does that make sense? Okay. So it's nice to know when things are increasing, when things are decreasing. It's not all that difficult. Okay. What we've got is we start with our entire domain. So would you guys agree that the entire domain of this graph here is A to D? Okay, so that's our A value. There's our D value. Now, what are those are numbers, right? Whatever they are, that is the domain. Okay. The next thing that we do is we want to, and this is the place that calculus is going to streamline this and make this a lot easier, is that we're going to find some key points like B and C. Okay? Point B here, okay, is called a maximum. Okay? If it's parabolic, we've talked about our maximum being the vertex, right? And we have the ability of finding that by taking the opposite of b over 2a. And that'd be the x value of our maximum. Okay? Well, other functions, maybe this is some type of cubic function, other functions have different ways of finding those maximum minimums. Okay? Calculus kind of targets that. Okay? Finding what we call derivatives will target that. You'll do what's called the first derivative test and second derivative test, and they will allow you to quickly find the location of point B and also the location here of point C. What do you think we're going to call point C? That is a minimum. Okay? Now, we'll get into a much more detailed discussion about maximum minimums, but those are referred to as local maximums and local minimums because they're not the largest value on the entire graph. Does that make sense? They're not the smallest y values on the entire graph, but they are the largest kind of in their vicinity. They're the largest in their little neighborhood, okay? Or they're the smallest in their little neighborhood. So we'll talk about that here in a couple slides. But once we find those, okay, would you guys argue that point B is kind of a transitional point? To the left of point B, you'd be walking up that curve, right? You'd be increasing. You get to B, kind of at the peak, right? At the top, and now you start walking to the right, you're descending now, right? So decreasing. That's the idea. What we're doing here is when we ask ourselves where okay, they'll say, you need to write this down. This is important. People mess this up a lot. Where or when or on what interval. Okay, so those are the three types of questions they'll ask. Where, when, or on what interval is the function increasing and they'll ask ask and decreasing, or they might just ask, where is it increasing, or where is it just decreasing, that kind of thing. Okay? So when they ask that, the answer to that, guys, so the when, the where, on what interval, what that is referring to, our answer is a series, maybe an interval, of domain values. Remember, those are x values, right? However,
What's that one word on the month?
that conclusion is determined by the behavior of the y values run out of room for the y values with respect to those x values. Okay, so and when I ask you where is this thing increasing, your answer to that is going to be a list of x values. I'm going to write it in an interval, okay? But you make you decide, or the determination of what x values to use for increasing, that is determined by what the y values are doing with respect to those particular x's. Does that make sense? Okay? So you're looking, the y's are telling you increasing or decreasing, but the answer that you give then is the x values in which that increasing is happening, or the x values in which that decreasing is happening. Okay? So, if I were to look at this graph, what we end up doing, okay, is once we find our maximums and minimums, then we know, because that was a change in behavior from increasing to decreasing or decreasing to increasing, we start looking at successive x's. So maybe I call that x1, and maybe I call that x2, okay? And I look at the y values that go with it. So this would be f of x sub 1, and this would be f of x sub 2, right? Would you guys agree that x sub 1 is less than x sub 2? Okay, so when that's the case, when your first input value is smaller than your second input value, and your first output value, f of x sub 1, is less than f of x sub 2, would you agree then that to go from f of x sub 1 as a y value to f of x sub 2 as a y value, you have to climb? You have to go up?
Right.
That's pretty obvious, right? That's kind of what I'm saying, is that this stuff hopefully is an elementary concept, but we've got to use the notation, the algebra, to express it. So we're saying whenever x sub 1 is less than x sub 2, whenever you have two x values in which the one on the left is smaller than the one on the right, which is obvious, when you plug those in and you find your y values on your function, if your first y value is less than your second y value, then you've got to be increasing. Okay? So if I ask you, where is this thing increasing, you're going to tell me the x values in which it is increasing. Okay? So, of this domain, would you guys agree that between A and B, these y values are always increasing? Okay. So A to B is going to be my first interval that I'm increasing. Now here's the thing. We're going to consider these open intervals. Okay? For the main fact that when I get to B, how would I decide? What would be the determination to say, oh, include B on the on the incline, on the increase, but exclude it on the decrease. Well, why would we do that? What would be the determining factor that says, well, keep it for increasing, but kick it out for decreasing, or keep it for decreasing, kick it out for increasing? Because it's really not part of either. Does that make sense? To the left, you're increasing. To the right, you're decreasing. At point B, that x value of B, you're not really doing either of those things. Okay? So we like to use open intervals. Okay? Inclusiveness is not warranted here. Same thing for the initial A value. Okay? My initial x value there. Just going to exclude it. So when we're doing increasing and decreasing, guys, I want to use open intervals. Okay? Always. Don't even worry about brackets here. Does that make sense? Okay? Because the bracket is ultimately a maximum or minimum point. Okay? So we don't want to include it on whether it be decreasing or increasing. But is there other places here that we are increasing? C to D, right? All right, so what we want to do is identify that it is increasing from C to D as well. But when I have multiple intervals and I have increasing in both those intervals, so I'm increasing between A and B or increasing from C to D, right? So what do I have to do with those intervals when I have something like that? You need to union them, okay? And remember what that means. It means that I am increasing in all of that information. All of those intervals, we're doing that. Our y values are portraying that behavior. Okay? So what then is happening here? Decreasing, right? So we're decreasing between B and C. One maybe situation we might see in some graphs, we did those piecewise functions, right? And some of those piecewise functions have horizontal components, correct? If it's horizontal, is it increasing? No, it's not decreasing though either, is it? Okay. What is it? It's horizontal. Constant. Okay. So those are things to kind of remember as well. Now, what I want us to also understand here, I'll kind of come to the side and draw this. Our increasing and decreasing concepts here, guys, we have to first understand where our minimums and maximums are for this particular reason. And then I'll try to keep this as something like that. So this is, we're going to say that that's a y value. So that'd be a y value of 2. So 3, 4, 5. That's an x value of 1. 2, 3, 4, 5, 6, 7. Okay. So I'm going to call this x sub 1, and this is x sub 2, right? Would you agree that x sub 1 is less than x sub 2? That's true, right? So then if I find this value, this is f of x sub 1 is equal to 2. And this value here is f of x sub 2, which is 5. You would say that 5 is greater than 2, correct? So your argument would be that on x1 to x2, we are increasing. Does that make sense? But are we? No. Collectively, from the first x value I evaluate and then the second x value I evaluate, I do get to a larger value in the x2 value. But there are other behaviors that are existing within here. So in order to make an accurate argument of whether I am increasing or decreasing, the first thing you have to find are these maximums and minimums, because those then tell you the accurate place to put x1 and x2. Does that make sense? Okay. Now, Is this, and we'll talk about this in more detail as well here in a little bit, but is this the largest y value on the entire graph? You would agree that that's probably the largest one, right? Okay. So this one is what we call a local maximum. Okay. Now think about local, it means the nearby area, right? Okay. So that would be the largest y value in comparison to the y values that are around it in kind of a close vicinity. Does that make sense? Okay, if we were to zoom in on just that part, and the zoom function on this doesn't work all that great, and go slow.
Can I go to the bathroom?
Yeah. All right, so if I just zoom in on that portion of the graph, and this is a calculus concept, being able to zoom in on just one portion, okay? Is that going to be the largest y value in that neighborhood?
Yeah.
Yeah, okay, it's kind of like a cropping technique, right? The calculus concept, you guys, is if I start zooming in far enough on that curve, I'm going to see just a line, right? Okay, if I take a circle and zoom in on any portion of that circle far enough, that circular portion is going to turn into what looks to be linear if my points are close enough. And that's the idea about calculus, is that if we do that enough, we should be able to transform every curve into something that we can analyze with linear approaches. Find out where that was. All right. So that's called all right, a local maximum. Okay. Now, would you agree that this is for the points that are around it? Would you agree that that is the smallest y value for the points that are around it? Okay, so I'm going to call that a local minimum. Okay. Would you agree that that also is a y value in which it is greater than any of the y values that are around it?
Yeah.
So we'll call that a local maximum. Okay. Now, I'm going to readjust my thinking here a little bit. I've identified my maximums and minimums. And I'm just going to say they're local because they're the maximum for everything that's close to them. But let's look at that pink one. Is that the smallest y value on the entire graph?
Yeah.
Okay. So we can better classify it. Instead of calling it local, we're going to use the word absolute, or you might see the word global. Okay? Those two words mean the entire thing, right? So that is the minimum of the entire graph. Okay? We'd probably even argue, I didn't highlight this one, but that point at 1, 2, that point right there would be a minimum, right? Okay, it would be a local minimum, right? So this is a local minimum, that's an absolute minimum, okay, or a global minimum. What about which one of the blue ones is the absolute? The one on the right, okay? So they're going to ask you to be able to identify those things. I can't remember which term our textbook uses, absolute or global. I've used so many textbooks over the years. But you'll be able to jump back and forth between those two terms, absolute or global, maximum and minimum. And that just basically means, by definition, that y value is greater than any other y value on the entire function. Okay? This y value is only greater than the other y values that are around it. Okay? This is, and we've already talked about this in detail, so I'm just going to put it up here, and just kind of talk about how concepts in mathematics are presented to us. And in Algebra 2, Geometry, we spend a lot of time working with things like this, more geometric phrases though. Algebra 1, you're pretty much just shown what to do, when to do it, but never explain like this is what governs these steps. And I think a little bit of that happens in Algebra 2 as well. But as we move on and we start becoming more independent in our math learning, I think it's important that we be able to read what these statements are saying so that we can, maybe I end up in a math class at college and they don't offer it at any time that I can go to class. Maybe I've got conflicting things and I got to take that class online. If you take an online math class, you're a pretty tough person because they're very difficult, okay? Because it's a lot of independent learning. It's taking phrases like these and seeing what do they really mean to me, okay? So I want to try to teach you guys over the course of the year, try to be able to interpret what these are saying because they're saying actually some pretty basic things, okay? But they're done in kind of a cryptic way. And the reason we do this, think about what we talked about in geometry. When we make a mathematical statement, whether it be a definition, a theorem, a postulate, whatever, we want to make sure that we make it so there's no vagueness, okay? So there's no imprecision. So that the fact that when we're trying to classify something or make a statement about something, we don't accidentally include something to be increasing where indeed it is maybe decreasing, or we don't want to accidentally classify something as increasing where it's actually constant. Does that make sense? So this is the algebraic way of doing that, and to make sure that nothing accidentally gets incorporated, okay? So here you see it says f is increasing, so it's going to be able to tell us that relationship. How do I know that a function is increasing, okay? Well, they're going to say on an interval I, all right? So capital I is usually what they'll do.
Pardon the interruption. This is just a reminder to all seniors. You do need to report to the auditorium for Wildcat time to meet with Jostens today. Again, that is for all seniors. You will be meeting with Jostens in the auditorium during Wildcat time today. Thank you.
All right, so they use a capital I, italicized I a lot of times to represent just some generic interval. Here, because I'm using x1 and x2, maybe they would write this in maybe a different textbook. They might say f is increasing on an interval x1 to x2, open interval, so I don't include the actual values x1, x2. If when I insert x1 into my function, I get a y value. Remember, this is a y value, right? F of x sub 1. That y value is less than this y value, okay? When the x's that you chose were in that relationship where x sub 1 came first on your number line and x sub 2 came second. Does that make sense? Okay? So what that's saying is if you know that x1 is to the left of x2, that is what that is saying right there on this interval. And if you plug x1 into your function and you get a y value, okay, which is f of x sub 1 here, and that y value is less than the y value when you take the second x, the one further to the right. Okay, if the first one is less than f of x sub 2, that y value, then doesn't it mean that you had to go up to get to that point from the first one? That's what increase, that's how we define increasing in algebraic terms. It would be much easier to say if y is, if the second y value is bigger than the first y value, okay? But if we do that, if that's the way we do it, there are situations that becomes ambiguous. That becomes imprecise for us, okay? The reverse of that says then, okay, well, if I just flip the inequality sign, okay, and my first y value is greater than my second y value, then we'd be decreasing, okay? Does that make sense, everybody? All right, I want to be able to attack those type of statements kind of all year long and get us to be able to read those mathematical statements. The next thing asks us to just take this function, which is that function right there says 12x squared plus 4x cubed minus 3x to the fourth. Now that function is a quartic. It's a fourth degree polynomial. All your fourth degree polynomials are going to look like this. It might be like, it kind of looks like an M, right? Some of them will look like W's depending on their concavity, depending on whether the leading term is positive or negative. Now this is actually the leading term because it's the largest exponent, okay? But they're going to ask you on what interval is this thing increasing or decreasing, okay? Well, the first thing to do is to find its maximums, right? Okay? Now, calculus will allow us to do this much quicker. We don't have a hand or analytic algebraic technique, handwritten work that's going to show me these points right there, okay? Until we get to talking about derivatives in calculus, okay? We might touch base with those a little bit later on in this class, but not much. Whoa. All right, so what would you call that point right there? Local maximum. Now, the position of the local maximum is an x value of -1, right? But the maximum value is 5. Okay? If I look at highlight that point, this is where the maximum occurs. This is the value that the maximum is. Does that make sense, everybody? Because remember, the maximum is determined by the y value, right? All the other y values in that area are smaller than 5. This point here would be a local minimum. That point there would be that's a global maximum. Okay, it's, I don't know, 30 something, but it's the largest y value on the entire graph, right? Now, the other ones that I gave you, the other example we did, had an absolute maximum and also had an absolute minimum, right? Does this one have an absolute minimum? The argument, people that would say yes would say, well, it's negative infinity. And then my argument is going to be, well, okay, then tell me what that number is. You can't, right? You can't define what that value would be. So in this case, we don't have an absolute minimum, okay? We do have what we call end behavior, and it says basically that the y values are going to negative infinity as our x's go to positive and negative infinity as well. But we're not going to classify infinity as a global maximum or global minimum, okay? When we talk about maximum minimums, we want to have a concrete value. We want to know what is that maximum, what is that minimum. In infinity, we can't do that with. Okay. I'm going to open up a assignment that targets this stuff. Shouldn't be anything that's extremely difficult. My plan for tomorrow, guys, is a short, maybe 15, 20-minute quiz over the piecewise function concepts.
For those students that have Mr. Miller and Mrs. Hartzler, you will be having Wildcat time in the cafeteria. So Mr. Miller and Mrs. Hartzler's classes will be reporting to the cafeteria. And also there is a college representative from BGSU who is going to be in the high school lobby for those interested in going to Bowling Green. Thank you.
Okay, so tomorrow's quiz. Piecewise functions. Evaluate piecewise functions. Okay, so if I give you like 3 or 4 rules and I ask you, well, what's f of 2, what's f of 5, what's f of 7? Okay, we'll plug those in. And then probably give you 1 or 2 domain questions that you have to tell me what the domain is, maybe graphically, and maybe 1 where you have to tell me what the domain is algebraically, like taking the function. Make sure we divide, don't divide by 0, and that sort of thing. Have a great day. Nate, you got your quiz. The video to that, the key is in your email. Same thing, Jenna. Picking your nose?
No, I'm sick and I keep like sniffing it back in and it gets too dry.
You want some tissues? Take with you? All right.
I I completely forgot to do it. So like, whether or not it's graded, I don't care. Can you just put it back up so
Okay, guys, I want to go over the test with you. If we look at question number 1, it's talking about vertical angle, so you're going to take x plus 93 equals 4x. 93 equals 3x. So then 31 is equal to x. Plug that in here and there. Both times you're going to get 124 back with those values. The vocabulary ones I'm going to skip over and let you do those on your own. Hopefully you've realized that there are some places on my website that lay out the vocabulary in a very nice manner for you. All right, so this one here is identify the hypothesis and conclusion. So remember, the hypothesis comes after the word if. Conclusion is after the word then. Okay. Here, I think the best thing to do is to look at this phrase and then say, okay, which one of these A, B, C, or D says this? So it says the conclusion is the part Q following then. Okay. So if a statement has a conclusion, then it is not the part. Okay. So if I read that, that doesn't make any sense. No, nowhere in this does it have the word not. Okay. If a statement is not, so again, we get to the first, there's no not in the blue. If a statement is the part Q following then it is a conclusion. If a statement is a conclusion, then it is the part Q following then. Okay? If the conclusion is the part Q following then. The conclusion is the part Q following then. So I believe that this would be C here. If a statement is the part Q following then it is the conclusion. Okay? That is what this statement is saying. Okay? So this is kind of a definition almost. Okay? Number 13. Okay, if I'm in Mississippi, then I'm in the South. So I've got not very good at this. We'll draw a rough sketch of the United States. Good enough. All right. We've got the North, we've got the South, and right here is Mississippi. All right. So if I am in Mississippi, so it says write the converse of this. The converse says if I am in the South, then I am Mississippi. Remember, the converse is just to take the blue and the green and flip them. So I'm going to look for a statement that says if I'm in the South, then I am in Mississippi. And here it is. Now I have to determine if that's true. Okay. Well, if you're in the South, does it mean, so being in the South, does it mean that you have to be in that region right there? So I would say this is false. I can be in Alabama and still be in the South. I can be, Alabama should be over here on this side of Mississippi. But yeah, that's my counterexample. Okay, so false, and that's my counterexample. The next one says write the inverse of the conditional. So the inverse just says if I am not in Mississippi, then I am not in the South. If I'm not in Mississippi, does it mean that if you're not down here, then you can be up there? Or that you have to be up there? Okay, because I can be not in Mississippi, and I can maybe be in Texas. Okay, so this would be, if I am not in Mississippi, then I'm not in the South. That's option B here. But then the inverse, that's going to be false because I can be in Alabama again and still be in the South. So there's my counterexample. It says write the contrapositive. Contrapositive would be taking, let's see here, taking this, so this is the converse. You'd be taking this statement and putting not here and not there. So if I am not in the South, then I am not in Mississippi. So it's saying if I'm not in the South. So if I'm not in the South, I cannot be in any of these areas here. So then it has to put me up maybe in the North. Well, if I'm in the North, there's no way they can be in the Mississippi. So that's got to be true. All right, so the contrapositive is true. Another way of answering this one is to know that the conditional was true, so then the contrapositive has to be true because they're logically equivalent. These types of questions are really the same, but now more math, okay, more math ideas. So it says if this is a conditional, okay, if A does not measure 38 degrees, then A is not acute. So that's the inverse when we negate both parts. If A is acute, then if angle 1 is acute, then angle 1 measures 38 degrees. That is the converse. That's the flip-flop of the if and then. And if A is not acute, then, angle 1 is not acute. I don't know why I keep saying A. If angle 1 is not acute, then angle 1 does not measure 38 degrees. That's the flip-flop and the negation. That's the contrapositive. So conditional is true. Conditional is true. Okay, if A measures 38 degrees, it's acute. So the conditional is true, so automatically the contrapositive is true. The converse, if A is acute, then measure of angle 1 has to be 38 degrees. Well, that's false. We could have other angles that fall in that acute definition, so that would be false. So then the inverse is also false. Same thing going on here. If M is the midpoint of segment AB, then M is between A and B, and AM is equal to MB. That is the conditional, and it is true. Okay, this is the definition of a midpoint. Okay, if M is between A and B, and AM equals MB, then M is the midpoint of segment AB. That is the converse. Okay, if M is the midpoint of segment AB, then if M is not the midpoint of segment AB, then M is not between A and B, and AM does not equal MB. That is the negation of the conditional, which we know is to be the inverse. That makes this one here the contrapositive. Now, if I answer the converse if M is between A and B and AM equals MB, so here we got A, B. They're saying M is between to the point where we get that. Well, that means that has to be a midpoint. So this would be true. The converse is true. The conditional is true. So if the conditional is true, the contrapositive is true. The converse is true, so is the inverse. All right, so running through these, this is the reflexive. This was symmetric. This here is we divided both sides. This is distribute. This here, all we did was took this y and rewrote it with what it was equal to and got that equation, so that's substitution. Here is if A equals B, but B equals C, and C equals D, we can go all the way from A to D and get that argument. So that comparison is the transitive property. If x plus 5 equals 16, x equals 11, that's subtraction. Here, this is multiplication. And if A equals B, then A plus 5 equals B plus 5, that's the addition, property of equality. If angle 1 and angle 2 are supplementary, then by the definition of supplementary angles, they add up to 180. If angle 1 and angle 2 are linear pair, then angle 1 and angle 2 are supplementary. That's the linear pair postulate. This is the definition of complementary angles. And then this one here is the definition of right angles. This one here, if AB is congruent to WZ, then AB equals WZ. That is the definition of congruence. Here, so remember an if and only if statement is a biconditional, but if I take the words if and only if out, put the word then in, if this, then that is true, but then the converse of this is also true. Those are the two things that make up this biconditional. So I'm going to find this one, if x squared equals 121, then x equals 11 or negative 11. Now I'm going to flip it, find the converse, which would be that one there. So those are the two that make that biconditional. This one here, remember if it's the law of detachment, we're looking for this first statement here. A doctor suspects her patient to have a broken arm, and then we look at this, and they have to match. This is our second statement. They have to match. The if part and this second statement have to match. Well, this just says nothing here about having a broken arm or a broken bone or anything like that. So there'd be no conclusion here. So it's not possible to make a conclusion using the law of detachment because the second statement does not match the hypothesis again. So we're looking at point or option B there. Here's the law of syllogism. So if Diane gets a new job, then she will need new clothes. If Diane needs new clothes, then it'll cost her money. So the idea is, law of syllogism is that a hypothesis and a conclusion need to match. So here, this conclusion matches that hypothesis. So the remaining statement that you get, okay, if I were to start with the original, or the first hypothesis here, and then go down to this conclusion, that would be my new statement that I got to find out here in A, B, C, and D. Working on this one, okay, if we've got angles that are supplementary right here, then we always create that by the definition of supplementary angles. All right, now, if I look up at my picture, CDE is that angle there. So they replace CDE there with X. DEF is that angle, so they replace DEF here with 5x minus 60. Well, if I replace things with what they're equal to, that's substitution. They're going to combine like terms here, and we talked about how that's the distributive property. Then from this line to that line, they just add 60, so that's the addition property of equality, and then they divide both sides by 6, so division property of equality. All right, so they're asking here, the scroll doesn't want to work. All right, it's better. N is congruent to Y, then Y is congruent to N. If you flip-flop them that way, that's just the symmetric property of equality. Now you might have gotten a different reason here, and it might have maybe shown up the transitive. This is the test that it generated for me, so you might want to run through all your different types of properties if you struggle on question 21. This one here, C is the midpoint of AD. Okay, and this is given. And then because we know that's a midpoint, we use that vocabulary word here, definition of a midpoint. Then they say, okay, if that's true, if it's congruency, then we can go to equality through the definition of congruence here. And then if AC up here in my picture is 2x, let's replace that AC with 2x. If CD is negative 2x plus 28, let's replace this CD with negative 2x plus 28. So that's substitution. All right, they're going to add 2x to both sides, and you should get 4x equals 28. That's using the addition property of equality. Then you divide both sides by 4, so that would be the division property. Reflexive property says angle K is congruent to angle K. Use a symmetric property, says if angle R is congruent to angle, or sorry, angle Y is congruent to angle R, then angle R is congruent to angle Y. More conditional statements here. So this is conditional. It says if two angles form a linear pair, then they're supplementary. That's the linear pair postulate, so that's true. If two angles do not form a linear pair, then they are not supplementary, so that is the inverse when we negate both parts. If they are not supplementary, then they do not form a linear pair. That is the contrapositive, and then this would be the converse. Okay, the conditional was true, so the contrapositive is going to be true. Now I got to answer whether this one is true or that one is true. I don't like this one because it's got the word not in it, so I'm going to answer this one. If they are supplementary, then they form a linear pair. Then we're saying that if any two angles are supplementary, they have to be a linear pair. And we know that maybe if that's 130 degrees, and maybe that angle is 50 degrees, they're supplementary, but they're not together making a linear pair. They don't share a vertex, and they're common side, and they're non-common sides form a straight line. They're separate angles, but they're still supplementary. So the converse is false, therefore the inverse is also false. Okay, I'm kind of running out of time here, so you're going to approach these things the same way. Okay, determine on which one's the inverse, which one's the converse, which one's the contrapositive, and then answer the truth values based off those. Same thing here. Okay, this is a vocabulary, 28 is a vocabulary, 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 and I told you guys in an email that I wiped that one away. So don't worry about that question. I gave all those points back, and that will not show up on the retake.